Labeling large-scale point cloud data for 3D understanding is expensive. Since image datasets are large and diverse, a recent direction focuses on learning 2D representations from images using self-supervised methods and then utilizing aligned image and LiDAR datasets to learn 3D representations by distilling 2D representations. Autonomous driving datasets, however, suffer from abundance of self-similarity and severe class imbalance, which limits our ability to transfer rich representations to 3D networks. To address these challenges, we observe that image representations at the superpixel level provide informative semantic clusters, which we use to design a loss that first reduces the contribution of false negatives and then balances the loss by estimating a proxy for the semantic distribution of contrastive pairs. The current state-of-art method for image-to-point cloud distillation is SLIDAR. This method is mainly designed for sparse LiDAR data. The idea is to use unsupervised segmentation methods to segment images into superpixels. Using superpixel masks, the image and point cloud feature maps are pooled to extract superpoint and superpixel embeddings. Finally, the task of the point encoder is to discriminate corresponding superpixels using superpoint embeddings via contrastive loss. Constructing semantically coherent image and point regions leads to learning useful object-level rather than point-level representations. To address the challenge of sampling positive pairs in sparse point clouds, SLIDAR breaks down the scene based on superpixels, which leads to contrastive pairs covering the entire 3D scene. Each pair has the same weight in the contrastive loss regardless of the density of the points. However, none of the previous methods in the literature consider the high level of self-similarity in autonomous driving datasets, which leads to a high number of false negative samples in the contrastive loss. In addition, these datasets suffer from severe class imbalance, leading to a loss that's dominated by well-represented contrastive pairs. The success of the contrastive loss has been attributed to its hardness-aware property. A study investigating the behavior of contrastive loss through the lens of the temperature scaling parameter shows that reducing the temperature increases the relative contribution of the closest negative samples. This hardness-aware property leads to pushing away the closest negative samples and is one of the main ingredients for the success of contrastive losses. Here we present the class distribution of superpixels from the new scenes dataset. We observe that a high number of superpixels belong to the same class. Unlike ImageNet dataset, which has 1,000 classes, autonomous driving scenes are a lot less diverse, leading to abundance of self-similarity. On the top row of this image, we present an image with a red marker on a road and a vehicle superpixel. We also show the predictions of a panoptic segmentation network. On the bottom row, we compute the cosine similarity relative to each marked superpixel. All superpixels, except the marked ones, are considered negative samples by the contrastive loss. Due to the hardness-aware property of the contrastive loss, we reason that the loss is dominated by gradients from semantically similar negative samples. This results in disturbing the local semantic structure of the learned 3D representation. Another challenge is the severe class imbalance. For example, dynamic objects like vehicles and pedestrians are severely underrepresented compared to background classes like road and vegetation. In the context of supervised contrastive learning, the long-tail problem, if left untreated, leads to poor performance on the underrepresented classes. Therefore, we reason that pre-training is dominated by well-represented samples. We hypothesize that self-supervised image features form semantically coherent clusters. We test this hypothesis by visualizing superpixel features using t-SNE and colorizing superpixels with their associated LiDAR labels. We use different self-supervised frameworks and show a clear semantic structure at the superpixel level. Now we can use this semantic structure to reduce the contribution of false negative samples and to balance the contribution of well-represented versus underrepresented samples. In order to address the issue of self-similarity, we rely on the prior semantic clustering of self-supervised image features and use cosine similarity of superpixel features as a measure for similarity between two image regions. We can then directly incorporate this similarity measure in our contrastive loss to reduce the contribution of negative samples that represent image regions that are semantically similar to the point regions. By doing so, we improve the semantic consistency of the learned 3D representations. We find through experimentation that the values of similarity might not be well calibrated to be directly used in the contrastive loss. Each pre-trained self-supervised backbone generates a different similarity profile. We hypothesize that the order of similarities is more consistent between 2D pre-trained models compared to the absolute values of similarities. To improve generalization to multiple 2D pre-trained models, for each positive sample, we propose to remove the k-nearest neighbors from the set of negative samples based on the similarity values. We find that this loss is better at transferring knowledge than directly downweighing the contributions of negative samples. To address the issue of severe class imbalance without having access to labels, we reason that superpixel to superpixel similarity can also be used as a proxy for class imbalance. For example, for a well-represented sample in a batch, its associated superpixel feature will have high aggregate similarity with all negative samples, while an underrepresented sample will have low aggregate similarity. To balance the training, first we compute votes for each sample based on aggregate similarity with negative samples, then we apply min-max normalization. Finally, for each positive sample, we assign a weight that's inversely proportional to the aggregate similarity to reduce the dominance of well-represented samples. Our models are pre-trained on Nusin's dataset and evaluated on Nusin's, Kitty, and Waymo datasets in fine-tuning setting. In addition, we conduct linear probing experiments on Nusin's dataset. As we can see, cross-modal frameworks like PPKT and Slider learn significantly better representations than lidar-only frameworks. We can also see that SD-Slider results in better linear separability and fine-tuning performance compared to Slider. We also conduct an experiment to study which semantic classes gain the most from our proposed loss. We create two sets, the minority set, which contains all classes with fewer than 5% of the superpixels in the pre-training set. The remaining classes are added to the majority set. As we can see, SD-Slider learns better representations that significantly improve semantic segmentation performance on the minority classes with almost no degradation on the majority classes. We also show that SD-Slider improves 3D representation learning by distilling image representations from different self-supervised frameworks. Thank you for listening. For more details, please refer to our paper.